Okay. So our next assumption axiom is the Born interpretation. So what the Born interpretation says is that if I have a wave function, then if I take the mod squared of that wave function, then that gives the probability density. Okay? It's not the probability, it's a probability density. So that means that if I ask, what is the probability of finding a quantum particle in state psi x of t at a position, say x, at a position x in a small volume, say d cubed of x, then the probability, if I ask what the probability, okay, then the answer is probability of finding the particle x d cubed of x is psi of xt mod squared d cubed of x, okay? So that is what we mean by a probability density, right? In some sense, this is the bucket, right? In which, okay, is this clear?
Yes, sir.
Okay, so, from Schrodinger equation, we can derive the following, so, okay, the probability density is often called rho x of t, and from Schrodinger equation, we can actually derive a differential equation for this guy. And it's an equation for an incompressible fluid. Okay. So this is the continuity equation. And this is in case this equation is valid in the absence of any sources or sinks. Okay, if there's a source or a sink, the right-hand side will not be zero. Here, rho is psi star, psi squared, and the current density is h bar by m, the imaginary part of psi star, gradient of psi. Okay. We derived this earlier in the course. So the normalization of the wave function is d cubed x, size, well, let's just write it in this new notation, which is rho x of t. And, initially it looks like, and it's integrated over all space. So this looks like it's time dependent, superficially. This looks like it's time dependent. But if you apply, if you integrate this equation, then you actually get this, and then using Gauss's theorem and the fact that psi is square integrable so that this goes to 0 as x goes to infinity, using that, you can show that the normalization actually does not change with time. but it's only in case there is no source or sink. Okay.
So what does it mean to have a source or sink in a wave function?
Yeah, well, it means that you basically have a, suppose you are creating particles, right? You have some energy being pumped into the system and you're creating particles, or you've defined your system in such a way, suppose you have defined your system in a way and, and there is, from outside the system, particles are coming in, okay? So in that case, your equation of continuity will not be given by the one that I showed above, right?
Okay, sir.
So, and then, this will not hold as well. And also the other thing is that suppose that you have a drain here, so that particles are going out. Then, if you stop the inflow of the particles, say, you don't have particles coming in anymore, then of course the probability of finding any particle in this region is going to go down over time, right? So the other thing is, so for example, there are, suppose you're describing some electrons, moving in some potential, but the potential has, say, some positively charged ions, right? And the electrons get captured by these ions and they become, neutralized, right? So that's another, but suppose that the way you've set up your equation, you are not looking into the inside of these ions. You're just looking at them as point particles. So that would be a case where you don't have, there would be sinks. These guys would be sinks of electrons, right? And you can model this sort of situation by allowing for potentials which are complex. Okay.